Hi, welcome to Teardown Tuesday. We've got another vintage bit of gear today, and it's from a CalLab, something you wouldn't ordinarily get your hands on. It's a resistance transfer standard. It's the Fluke 5450A, straight from the mid-80s, I think 85, 86, vintage, something like that. This would be the transfer standard used for calibrating multimeters back then. It's obsolete now, but you know, it's still not a bad bit of kit. And look at the size of it. It is absolutely enormous and designed to either go into a rack or be bench mounted like this. And basically, it is nothing more than a bunch of precision resistors in a box. That's pretty much all it is. Yes, it's got a big LED display on here which shows you the value, but it doesn't actually measure anything. All it is basically a bit of automated gear for automated testing of multimeters in a typical calibration lab. And the way it works is it's a 4-terminal capability, 2 or 4-terminal measurement. It's got really schmicko precision resistors inside, and when you calibrate this thing itself, then you actually program in the exact value of the calibration resistors in here. So this doesn't actually measure its own internal resistors. It can't actually do that, but what it can do is actually display the value. What use is that, I hear you ask? Well, in automated measurement with the upside down, all the electrons are going to fall out, GPIB on the bottom, you can automate the testing of this, and it can read the value out of this to know exactly what value the calibration resistor is in here, and then it compare it with the device under test and so on. So it's a really just a very fancy automated relay switching box, and it could be interesting inside, not only in the type and construction of the precision resistors, calibration reference standard resistors in this thing, but yeah, in the way physical construction and stuff like that, keep out noise, leakage, all that sort of stuff in the analog section of it. Could be really interesting. So, you know, we say in an EEVblog, don't turn it on, take it apart. And if we take a look at the specs here for it, I mean, it's, you know, compared to sort of modern multimeters, it really wouldn't be suitable for, say, calibrating a modern, well, probably not anyway, calibrating, say, a modern Agilent 34661A 6.5 digit multimeter or an equivalent digital multimeter. I mean, we're looking at, you know, nominal tolerances here of 50 ppm, something like that. Absolute uncertainty is actually quite good, you know, down in the order of 5 ppm or under for like 24 hours or 1 year, you know, 12, 13 ppm. And they're the various test currents. But, you know, compared with, say, my precision resistor box I've got here, which has just got a couple of $20 resistors in a modern Vichy resistor. There's the part number. Let's get the best one here, which is the 10K one. You know, we're talking 0.005% or 50 ppm accuracy. So it's sort of, you know, in the same order as this. And if you compare the stability, like for example a 90-day stability, you're only talking, you know, 3 ppm or something like that, really quite good. And temperature coefficient here, 1.5 ppm per degree C. And if you compare that to here, this is like, you know, 2 ppm per degree C. So, you know, it's not a huge amount better than just a modern, you know, precision resistor from the likes of Vichy that you can buy for like $20 odd. But, you know, in practice, I'd bet my money on the resistors in this box any day of the week. So this is basically a single-purpose resistance calibrator, only designed for calibrating the resistance, or calibration checking the resistance ranges of multimeters. That's it. Doesn't do anything else. Unlike, you know, modern multi-function calibrators that can do everything. You know, AC, DC, voltage, resistance, current, all sorts of stuff, like a Fluke 5700 or a 50A multi-function calibrator, for example. So they're pretty much made something like this obsolete. I'm not sure of a CalLab that would still be running one of these things, a 5450A, but if you are aware of any CalLabs still using them for a specific purpose, please chime in. But yeah, basically here is the control panel for it. It's designed for 2 and 4 wire measurement. It's got a 2-wire compensation function, which basically just doesn't do anything fancy. It just adds a pre-measured and pre-entered value on top of the actual internal calibration value in there. So it just adds a stored number basically to the value. And of course in 4-wire mode you would just hook this directly onto your multimeter. The sense wires go to the sense terminals of your multimeter. The output goes to the input terminals of your multimeter. That's it. It's also got a ground shield which you can turn off and on, external guard for when you're actually calibrating this thing, and I won't go into the whole way you would actually calibrate this in terms of shielding and everything else, but can be really, really important, that external guard shield. That's just not just mains earth willy-nilly. It's, you know, it has very specific requirements in terms of noise reduction for calibrating this thing, and then all you do is you just choose your range. And that's it. It's pretty basic. It's got a multiplier, so it can only select values of 1 ohm, 10 ohms, 100 ohms in each decade up to 100 megohms, but you can actually multiply that by 1.9. So if you wanted a 1.9K standard resistor, press that button with that one and you would get 1.9K. It'd switch the relays internally, clunk, clunk, and you'd get 1.9K reference resistor across there. And that's pretty much all there is to it. It'll also allows you to display the ppm error, but once again, it's not actually measuring anything. It is just displaying a pre-recorded value in there, and that's all it does on the 2, 4, 6, 8-digit display here. It can show the output value or the percentage error for there. And that's all there is to it. As I said, it's dumb. This display is not reading anything, just showing you a pre-stored value. On the back, nothing fancy, of course. Mains input, IEEE 488, GPIB standard, plus a set of rear terminals on the back for when it's mounted into a rack or something like that. Once again, these are low EMF connectors in there. You can see they're probably some sort of a tellurium copper or something like that. Really schmicko. I don't know, what are they worth, like $100 each to get a replacement set of those? And it's made in the United States of America. Still has the calibration void seal intact, but the thing has been opened. As you can see, it was calibrated by the Fluke metrology lab, but it has been opened. So inside this thing is going to be, I think when we open it up, we're not going to find anything fancy at all. We're just going to find some a whole lot of digital stuff, which of course drives the GPIB and the 7-segment displays on the front. Nothing doing there. That has, you know, nothing to do with the actual real operation of this unit. What we're interested in is all the precision reference resistors in here and the relay switching and all that. That will be probably triple shielded or something ridiculous like that, and it will probably be laid out quite well, because this thing, you know, if you open this thing and you breathe on it, you know, you're probably going to have to recalibrate the thing. I mean, especially when you're talking, or if you touch it, you know, all the grease from your fingers and stuff like that. Probably not if you breathe on it, but, you know, the oils from your fingers, if they get on and contaminate the analog board in here. Oh, here we go. Yeah, contaminate that analog. Aha, ta-da. Look at that. And there it is. Check that out. It's actually quite big. I've had to prop the thing up vertically on my bench here to take a look. And as I was saying, the oils and stuff from your fingers, if they contaminate the analog circuitry in here, as I said, you know, here it is behind all the shielding in here, leakage sensitive printed circuit assembly, use special handling. There you go. Because when you're talking about 100 meg, you know, a precision reference resistor, which is, you know, 0.005% accurate or something, it doesn't take much in terms of leakage for that value to change. Alright, let's just pluck a number out of our arse to see what sort of scale magnitude we need to get in parallel with our 100 megohm reference resistor for, you know, it to start being a problem. I chose my Casio FX61F because it has a parallel button, the only commercial calculator in existence that ever did, I think. Oh, beautiful. Anyway, 100 meg in parallel with, let's say, 100 gig. 100 gig ohms, okay? Let's have a look what we get. Look at that, 99.9 meg. We're still outside of our tolerance. If we go divided by 100 meg like that, there we go, subtract 1, and let's shift that, and times 100. What do we get in percentage there? We're talking, 0.1%. Okay, so that's, we're just, outside of our 0.05% or better. Just forget about it. So even 100 gig ohms in parallel with that 100 meg ohm reference resistor gives us that 0.1% error. Way out. We need something in the order of, even like tera ohms. Even a 1 tera ohm can actually affect this thing. And of course, that's aside from noise issues. I mean, we're at 100 meg at 1 volt. You're only talking 10 nanoamps. I mean, it's naff all, half a bee's dick. So really, any noise that gets into this thing can be a real pain in the ass. That's why that switchable earth terminal on the front panel is such a big deal. So this is really interesting. They've actually got a relay table here, which shows you which relays are energized for each of the particular ranges. A relay map. Look at that. That's just gorgeous engineering right there. So there's 34 relays inside this thing, and it even gives you the Fluke part numbers for the different relay types there. We've got ourselves what looks like the transformer box in here, and the internal voltage selections are in there. And look at this, thoughtfully provided 2 spare fuses in little holders on the side. Accessible. Ah, it's a thing of beauty. And really there's nothing exciting in there at all. We've just got some range selection switches for the mains range, and there's the mains transformer down there. But, the main point is it is inside its own shielded box. They're not taking any chances. And as far as the digital board goes, well, our care factor is around about 0 plus 50 ppm. I mean, it's not that exciting at all. We've got a Z80 CPU down here, and we've got some ROMs and some memory, and well, whoop-de-doo. I mean, all it's doing, there's some jumpers down there. That's some programmable jumpers, but really, we don't care. Ribbon cable going off to the front LED matrix display, and really we don't care. You don't need much horsepower at all to drive a GPIB, and then drive a display and store a value. So check out that monster mains filter cap though. That's absolutely insane. Manufactured by Sprague Compulytics. Geez, Sprague, are they still around? I don't know, but that's a 22,000 microfarad 15 volt cap plus 85 degrees C rated. Jeez, look at the size of it. What the hell do they need that for? It's absolutely enormous for the relay switching, I guess. Kerklunk. And we have ourselves a date code. Well, it's actually 1970s. Look, copyright 1979, John Fluke Manufacturing Co. So this model dates at least back to then. I mean, the user manual I got says, I double-checked out 1984. It doesn't say anything less than that. But we've got ourselves a date code. We're looking at, 1989 vintage. That could have been changed. But look, we've got 88 vintage parts. Bit of dust on this sucker, but yeah, so this thing was manufactured in late 80s, 89, maybe 1990. All right, let's lift the skirt up. This is what we want to see. I better not breathe on this thing. I better not sneeze, because we could be in trouble if I do that. I definitely won't be touching anything inside here. I have a poke around with the plastic stick. I was wondering why there's a hole in there. Well, the hole is a finger lift. Look at that. There we go. And I'll try not to spit when I talk too. I try not to get too excited and salivate over this thing. Here we go. Ta-da! Holy dooly. Look at that. Oh, look at those relays. Look at the resistors. Oh. If we take a look at the relays here, company I've never heard of, Potter and Brumfield. Whoa. To Google. Sure enough, Potter and Brumfield still exist, but, well, the brand does, but it's now owned by TE Connectivity. And yes, they still make relays. Oh, go figure. And as we saw before on the front panel, there are various types of relays in here. This one is a 4.5 volt DC one. Yeah, double pole, double throw, is it? And on the analog board, we've got ourselves copyright 1983. And down here we've got ourselves a bunch of unusual looking Kodo reed relays. Of course, Kodo, one of the best brands in the business in terms of low leakage, high performance relays. And these would specifically be low leakage types. Had a quick look of a data sheet, couldn't find the exact one, but I found A1240 Series 1 contact leakage in up in the order of power 10 to the power of 14. And I think I've done a video way back on relay matrices for measuring high value resistors. I'll try and find that and link it in. And now precision resistors in this thing, check them out. They are manufactured, well, I assume they're manufactured by Fluke. They've got individual part numbers, well, Fluke part numbers, I presume, and look, they've got two in this case, 40.5K, 0.005%. Technology, I don't know, some sort of wire wound. And the 0.005% does seem to be the best that they've got in here, we can see, but some are, 0.01. The ones that, aren't as critical, there's another couple up there, 0.01. 0.005 for 4K ones, 1.8K. Once you get down in those values, 0.1, there's another 162 ohms, for example. And here we go, these low value 40 ohm ones, 0.05% each, but take a look at the configuration. What we've got here is 4 paralleled 40 ohm resistors, so that gives us a 10 ohm better than 0.05%, and then that 10 ohms in series with another 10 ohm there, and then we've got then that is in series with 262 ohms in parallel. And check out the configuration. It's it's all over the shop. They've got some complex arrangement here, that's for sure. And then we've got some 280 ohms in parallel, and then we've got 1.62 Ks here, and then that's branching off there, and then 1.8K. So this really long string of precision resistors. Look at that, isn't that pornographic? Special low leakage Kodo relays. Well, of course, on the very high side resistor values. This one is, you probably can't see that, but that's 81 meg. There it is, and it looks like that is, you can check the arrangement down in here of this string with the relay switching in there, and they're 4.5 mega pop, and these ones here are, yeah, these are all 4.5 meg, getting down to 450K here. So this part of the circuit is where our leakage really matters. And you can see that they've conveniently marked the tap points. I mean, there's the 19 meg tap there, so when you include that 1.9 multiplier, when you switch that button on the front for the 1.9 multiplier, there we go, that tap for the 10 meg range, that's the tap it's going to use, and then there's the 10 meg tap there, and so on down the string. There's the 1.9 meg tap, there's the 1 meg tap. And you can bet your bottom dollar that they know the leakage of this board down in here, and the solder, it's got that crinkly solder resist coating on it. Fluke really would have done their homework on that, you can bet your bottom dollar. But of course, when you get to the really top end of the range, the 100 meg, the PCB itself is not good enough. You get too much leakage. What do you have to do? You have to have special low leakage insulators like that, with the copper removed from around there, and then you have to run insulated point-to-point wires like that right into special output relays like this. They couldn't, those Koto ones that we looked at weren't even good enough. These are Electrol brand ones. Whoa, look at those. How much do they cost each, or did cost each? There we go, Electrol brand, another one I've never heard of, R8538. Couldn't find any info on that on a first pass, except that Electrol were bought out by Hamlin. So, you know, I'm not sure if you could still buy those. So check it out. We've got the input coming over here, switching through here once again on these isolated standoffs here, or point-to-point wiring. They cannot use the PCB. This wire down there is sneaking off through a hole in the board. Nah, only air's good enough for this. And for those who love their connectors, look at that low EMF tellurium copper, no doubt. And in all the excitement over the pornographic relays, I missed this little kludge. Look at this, a 7805 Linear Regulator that was supposed to just probably be freestanding in the board there, or maybe, you know, attached to the back panel there. Look, it looks like they've done a staggered offset. Maybe they didn't get the PCB right to line up with the chassis or vice versa. So they've, I don't know, they've done a kludge there, mounting it up off the board. And there's a sill pad in there to insulate it from the back. But geez, look at that. And they've gone to the trouble to add a flat flex there. Unbelievable. I mean, it's not a huge amount of current, obviously, but you know, your guess is as good as mine. Who goofed up there? So you can really see the arrangement of the resistors here. I mean, here's our 10 ohm tap, 19 ohm tap, 100 ohm tap, 190 ohm tap, and so forth up there, blah, blah, blah. It goes around like that, comes down here like this. But what I don't see is, well, there's our COM. That says COM down there. There's our common terminal, but I don't see the 1 ohm tap. It's not there. And if you're curious, 10 ohms, the spec for that, or the nominal tolerance, is 500 ppm, or 0.05%. In terms of absolute uncertainty, we're down to about, you know, 40, 50 ppm, something like that. So that's basically, to get that 0.05%, we're looking at 5 milliohms maximum error there. So in terms of, you know, relay switching, going all the way through the wire into the front panel and all that sort of stuff, well, it doesn't have to be better than that, but in terms of the, you know, the stability, I mean, you can calibrate the uncertainty out of all that, but, you know, still, it's got to be very, very low. These relays have to be ultra reliable in terms of contact resistance. So I don't have the schematic for this one to hand. If anyone does, if anyone actually has the service manual which has the front end schematic in it, then that would be fantastic. The actual, you know, so we can see the actual relay arrangement. Wouldn't surprise me if they, you know, paralleled up some relay contacts or something like that for these really low order ranges. I can't imagine where the 1 ohm range is actually. Haven't found it yet. Shielded can. Wonder what's under there. Silly me, I did find the schematic in the operational manual for this thing. It was right at the back. I swore I checked it and it wasn't in there, but duh, it is. And ta-da, here's a schematic for the analog section here with all the relay switching and the wiring and everything else. Fantastic, all beautifully hand-drawn as you got back in those old days. So let's take a look at the string here. Here we go. Here's our 1 ohm resistor and our 1.9 ohm resistor up here, which we haven't found yet. I bet they're under that can for sure. And there you go. There's the 4 paralleled 40 ohm resistors that we got before, and then all the various points. There's our common terminal, so that's sort of on the, so these lower value resistors are on the flip side of that. And then we went up the chain, and we can switch various configurations of these resistors through to a high and low bus, very similar to what I've done in a previous relay switching matrix, which I said I'll link in, and I'll try and do that. And going all the way over to our final output, and check it out, there we go. Sure enough, they've identified on the schematic, look, they've put a circle around that which indicates to the PCB designer, you know, that is to be marked off the PCB. I'm not sure over here, number 1, so we're obviously got some detail we'll have to look at, but yeah, that indicates that that's raised off the PCB, and this is all just wiring. And there we go, they've got 4401 cable, they're specifying the type used over there, so all these high impedance parts are all mounted off the board. And it looks like I might be right in that they do use multiple relay contacts in parallel for the 1 and 1.9 ohm ranges. check it out. There we go, 3 in parallel on each line, just to get that contact resistance down and to within a manageable tolerance variation over the switching life of the relay. There you go, unless noted otherwise. There's our note for our points down there. Here we go, Teflon standoffs. There we go, 7 places resistors, specially matched set. There we go, R5 to R39. So R5, yep, all of these R5 through to R5, R6, yeah, so all of these are specially matched. So yeah, they don't just roll off the assembly line, they're probably individually hand tested, hand measured and sorted by, someone rubbing their grey beard as they do it, sorting them into the individual bins, and then, putting a bit of spit and polish on each one. Oh, beautiful. And you can see the beautiful soldered ends of the cans of those resistors there. Ah, just absolutely beautiful. Gold-plated pins. Oh, each manufactured and hand assembled by nude virgins in Utopia land. Just beautiful. If anyone knows if Fluke actually made these resistors themselves or still do roll their own specialty resistors, please let us know. So I reckon the the 1 ohm and 1.9 ohm resistors are under this can down in here. Does it have an extra relay down in there? I don't know. I haven't looked at the schematic yet. Dare I open this sucker? It's almost sacrilegious, isn't it? There's just a couple of big standoffs on there, and yeah, I mean, as I said, even at the 10 ohm range, only talking, what was it, 5 milliohms or something to get within that 0.05% band. And really, it's even going to be, well, it's an order of magnitude, actually, less for, oh, look at those, yes, wire wound resistors on card. Look at that. Now, I'm sorry that it's not easy to get in here, but look at the wire wound resistor. That looks like one big wide strap on a clear. You can actually see through it. You can see that's like some sort of a perspex acrylic sort of sheet that they've wound that on, but you can see that that's tape wrapped over there, and look, individually serial numbered down in there. Oh yeah, these things are definitely manufactured by nude virgins in Utopia land, that's for sure, and individually tested by greybeards, no doubt. Look at that, beautiful. They would have been manufactured in-house by Fluke, I'm guessing. And check out the dual terminals coming off that thing, both there and there on that side. They've just tapped these off individually right at the point there. Beautiful. Yeah, so that's probably some form of nichrome resistor. Wire, as in like a flat strip wire, and they've just wound that around that plastic see-through former there, and then they've just soldered. Sorry, it's very difficult to get in here, but then there we go, you can see the strap coming over and then soldered directly onto that dual point contact there. One of the interesting things to note is that they have socketed all of these low value relays. By low value I mean used on the low side of the resistor, low value resistance side of the reference string in there. And I would have thought that wouldn't have been the go. You would have soldered these directly onto the board, but that certainly makes them replaceable, and I'm sure those sockets are worth a fortune and gold plated to the hilt. And you might be wondering why it was shielded like this. Well, this sucker is a coil in there. You don't want anything getting in there. It's because, as we saw before, these are precision wire wound resistors. These are already shielded on one end of the can there. So once again, it's interesting to see the progression in the contact and resistor technology as you go up, right down at the low end here, special shielded wire wound, hand manufactured wire wound resistors down in here, and multi-contact relays down in here to ensure the tolerance of that. And then we've got some fairly beefy ones for the low value resistors on the precision string along here. So once again, you really need good top quality low contact resistance relays, possibly multiple contacts along there. As you go up, you know, in the tens of ohms, the hundreds of ohms sort of range, and then as you get up into the kilo ohm range, you can go for these smaller contact resistance. By smaller, I mean physically smaller relays. So, you know, probably not as great or as lower contact resistance as the other relays along here, not nearly as critical on these lower ranges down here. And then you get up to these Koto reed relays on the sort of the megohm range up here, where contact resistance doesn't matter at all. It's down in the noise, you can't even measure it. What matters right up at this end is the insulation resistance of the relay, which wouldn't have mattered for all these ones down here. Who gives a rat's ass what the insulation resistance of these relays is when it's in parallel with, you know, 1 ohm, 10 ohms, hundreds of ohms. But when you're in parallel with, you know, 10 meg, 100 meg, things like that, as I said, you know, tera ohms, gig ohms, you know, hundreds of gig ohms up into the tera ohms region actually matters. So that's why you need those very high insulation resistance values up here from contact to contact, you know, in terms of up to the point where it's not necessarily the relay that dominates, it becomes the PCB that dominates itself, the surface of the PCB. As I said, you know, oils from hands, contaminants from the air, other stuff. There's no fans in this thing, so, you know, nothing's actually blowing through this thing, but dust has accumulated to the point where down in this section with the really high values, we needed more special relays, reed relays again, and then Teflon standoffs on the board, so we can't rely on the PCB anymore right up at the high end. And that, as you progress all the way through, you've got different challenges at each design stage. Fantastic. So I hope you found that rather interesting. I certainly did. And, you know, there's more technology which goes into actually designing an analog section like this for one of these precision calibrators. Not only just designing, but manufacturing the precision resistors themselves. And as I said, if anyone has any info on manufacturing, Fluke manufacturing their own precision resistors in here, please let us know. So there you go. I love looking in high-end gear like this. You always find nice little, you know, design tweaks here and there to get these things, you know, to get the operational performance of these units. And this isn't even bleeding edge these days. I mean, this is late 70s, you know, early to mid 80s technology designed to calibrate multimeters of that era. You know, it's probably maybe not even good enough to, you know, calibrate a modern 6.5 digit multimeter like the Agilent one I've got there. So there you go. Unbelievably fascinating. I love this sort of stuff. And if you want to discuss it, best place to do it is the EEVblog forum, link below. As always, I'll link in any available data sheets and the manual for this thing, which has some beautifully drawn circuit diagrams for this thing in terms of like all the digital stuff, all hand drawn. Just beautiful. Really is. I love it. And here it is working connected to my Agilent 5450A 6.5 digit bench meter, and it hasn't been warmed up for long, but it doesn't seem to drift. Well, neither of them seem to drift much at all, really. So this is on the 1K. So as you can see, it's got programmed in as the calibration value is 1.000066K, and we're reading 1.000086. Not quite bang on, but you wouldn't expect it based on the tolerance. And I can change the range there, and you can see it seems to be on the high side for various I can go auto range here, but often it doesn't quite get the auto range quite right. And as you can see, this always seems to read on the high side of things. And point there, you know, there it is, 10 meg. Oh, that one's reading actually lower than what we're getting on here, but as you can see, a bit of noise on there. Probably have to do some extra power line cycles. And at 100 meg, it's reading low, but on most of the low ranges, it certainly seems to be measuring slightly on the high side of things. That one's almost bang on. If you see, the auto range doesn't quite work when it's on this thing, when it's right near to the full scale there. So we can actually change that. There we go. That one's reading slightly low, but most of the mid-range stuff seems to be reading slightly high. Now we're getting into tricky, real tricky business down in the 10 ohm range down in there. But as you can see, it's still within spec. Let's take 1K. Well, you know, it's within margins of this entire test setup. Let me give you an example here. Let's do this one and see how far we're out in terms of percentage. So we're looking at 1.000085, for example, divided by 1.000066, and we're looking at that, subtract 1, change the register there, and we're looking at times, change that to percentage, and we're looking at, you know, around about 0.00, let's say round it to 0.002%, or 20 ppm, and that is better. The difference there of roughly 20 ppm or 0.002% is within the 24-hour accuracy spec of my Agilent bench meter here. So as you can see, you know, which one's right, which one's wrong, you know, we just don't know. We would have to take this to a standards Cal lab that has an order of magnitude or better than this Agilent unit, and certainly at least maybe 4 times better, say, than this unit itself, to actually have it recalibrated. It doesn't have a Cal sticker, and I have no idea when it was last actually calibrated, and these values actually programmed into the thing. Have no idea. So who knows, it might have been 10, 15 years ago. I don't know, it may have been a couple of years ago. Got no idea. Anyway, it does work, but hey, because the resistors are ultra stable in this thing, we could just have this recalibrated. We just hook it up, take it to a standards Cal lab, program in the new values, and bang, I'm sure it's not going to drift a sausage. So as always, if you enjoyed it, give it a thumbs up. Catch you next time.